Now, in the previous example, we talked about this water pipe situation. We talked about voltage as being a pump and resistance as being the pipe. Okay? So, we talked, oh, well, you know, that pipe has an effect on things. You know, if you have gravel in that pipe, you have a filter in that pipe, there's all sorts of problems that'll slow down the flow that goes through there. If it's a narrower pipe, it'll slow down the flow. If it's a bigger, wider pipe, it'll allow more water through. So all of those things have an effect on the resistance value. Okay? So what we're going to do is we're going to come up with an equation to describe resistance. Now remember, resistance is the impedance of charge. It prevents charge from traveling through. Higher resistance means less charge. So the first term that comes in is rho. Okay? RHO. Rho is a material value. When you see rho on and off in the rest of your physics career, if you ever go on and do some hardcore physics, you'll see rho is referring to, like, in density terms. It's referring to a property. It's referring to a material. Here's a material. Here's its rho value. Here's its rho value for density. Here's its rho value for charge density. Here's its rho value. It's referring to a property of material. So whenever you see a rho, it's property. Okay? Now that times the length. Okay? So it shouldn't be that hard to imagine that a longer piece of pipe is going to have more resistance. A perfect example of that is take the Colorado River. You know, we've been tapping into the potential of the Colorado River by putting up more and more dams. We've been kind of increasing the resistance. So the Colorado River falls short. It doesn't quite reach the ocean anymore. It kind of just dies in the desert. So longer pieces gives it more resistance. It just doesn't have that last little bit of oomph to get through it. So it's going to require more pressure to get that water to travel all the way through it. Okay? So property of the material, the length of that material divided by the area of that material. And when we're referring to the area, we're referring to this section. That's the area, the cross-sectional area of that. Okay? So the resistance of anything can be measured by its property value, its rho value, times the length of that material divided by the area. Okay, so the length, obviously, is the length of this wire. Now I got a question for you, though. Okay? So if I had a fictitious piece of wire that looked like this, okay, that kind of expands out. Okay, so it balloons out. You can think of it as being an old luminescent light bulb filament, which eventually degrade until they get to very small points. When referring to the resistance that's associated with this material, what area would I use? Would I use this area or would I use this area? And remember, we're talking about property resist charge. Okay? This is going to be a greater resistance. This is going to be my total. When I refer to the resistance of this material, this is the cross-sectional area I'm going to be concerned about. This area is restricting the amount of charge that's allowed through. This area is not. So if you imagine charge being pumped into here, well, only so much can get through that hole. Even if I flip the sides and I said charge is being pumped into this direction, charge doesn't build up. It has to move. So it's only going to accept as much charge as it can get rid of. So it's still restricting the amount of charge going through there. Okay? So you're not going to get 12 arrows in and only 3 arrows out. You got to have that 3 arrows in and 3 arrows out. It doesn't build charge in a circuit. Okay? So anyway, that's a really quick equation that tells you what resistance is and how we find it. Okay?